portion of the second part of the course. All right, so let's begin, and so we are going to discuss what are called linear transformations today. Okay, so the linear transformation is something that you probably already know, right? Linear, so basically means like a line. You know, what is like a line, right? That is, of course, a question to be answered. So let us start with the definition of a linear transformation. Okay. So let's say we have two vector spaces, U and V. Okay. The important condition is, as you can read on the slide, that both of these vector spaces, U and V, are assumed to be defined over the same field. Okay, that is important. Once you have two such vector spaces over the same field F, a function from U to V is said to be a linear transformation from U to V if it satisfies these two conditions. Okay, so one is what is called additivity or additive. The second is what is called homogeneous or homogeneity. What does additivity mean? Means that if I pick any two arbitrary vectors x and y from my domain vector space U, then if I first add these two vectors in the vector space U, the domain vector space, and then use the function f to obtain an element in the codomain vector space V, that must be the same as if I first individually map the elements x and y to the vector space V and then perform this addition, okay, in the vector space V. Okay, so must be a little careful with the notations here. Again, I'm using basically something like operator overloading that you are possibly familiar with in object-oriented languages. This plus refers to the vector addition in the vector space V, whereas this plus refers to the vector addition in the vector space U. Okay, and in principle, you can see that what I'm trying to say over here is the additivity implies F from, remember, U with this vector addition, it forms an abelian group. V with the corresponding vector addition forms an abelian group. So what does one imply? This function f is supposed to be
Homogene.
sorry, yeah, so group homomorphism. Okay, so that is the first condition. The second is, of course, we are looking at vector spaces. So vector spaces have an additional operation defined on the set. So for every scalar that you can think of from the field F, which by the way is the common field, and for every x in the domain U, doesn't matter whether we first perform a scalar multiplication and then map the resultant element to the vector space V. That is the same as you first map the element x using the function f to the vector space V and then perform a scalar multiplication in the vector space V. Okay, so here again in the notation, this scalar multiplication is the scalar multiplication on V. This is a scalar multiplication on the vector space U. Okay, so in summary, what you can see is if group homomorphism is something that we can understand as a function that preserves the group operation. Similarly, linear transformation between vector spaces can be understood as functions that preserve both the vector space operations. Right? So in that sense, it is basically analogous to a homomorphism. And in fact, That is another term used instead of linear transformation. Okay? Linear transformations are also sometimes called vector space homomorphisms. Okay? They preserve both the vector space operations. So in that sense, if group homomorphism, we can sort of say that the forms or the structure of the groups are same, whether it is U or V. If they are homomorphic, we sort of understand that the group structure is similar, not the same. Okay. Similarly, if you have a linear transformation between U and V, right, the vector space structure is preserved. Okay, that is how one can interpret this. Any questions here? Okay, then small definition here. So as of now, we have defined what is a linear transformation. Okay. In general, linear transformations are understood to be between different vector spaces. Okay. The domain and codomain vector spaces are not the same. We in general call it a linear transformation. But if the domain and codomain vector spaces are the same, we usually, okay, this is not a hard and fast rule. Okay, we usually call the linear transformation as a linear operator. Okay, that's just a small change in the definition, but again, is not sort of very formal. Okay, this is something that I will be most likely using in the course. Some books I think will follow this, but some books may not follow this. Okay, so even if I use linear transformations instead of linear operators, don't get confused. Okay, the only difference is the domain and codomain vector spaces may or may not be different. Okay, then let's look at examples. Can you think of an example here? Anyone? Okay, let me think of a simple example. How about rotation by an angle theta? Okay, in your xy plane. Is this going to be a linear transformation?
Yes, sir.
Why? So, whenever you say this is a linear transformation, you will have to prove it. So, let's say I have a point xy, whose coordinates x and y coordinates are x and y, right? Where will this go? If I rotate this by an angle theta, assume the direction of rotation is anti-clockwise. Where will this point go?
X e to the power I theta.
E to the power I theta.
Oh
Or
no,
very
sine theta times x.
X cos theta minus y sin
minus
theta.
x
x
cos
cos
theta plus y
theta
z.
minus or plus?
So plus
Plus y sine.
Either both are same.
How can both of them be same?
so and then minus x sin theta plus y cos
Minus x sine theta.
plus y cos theta.
Y cos theta. So is this a linear transformation? Right? So you should formally verify both these properties. So you can take x1, y1 and x2, y2. Right? We already know what is the result of applying r theta to both of these individually. And you should now verify what happens if you rotate this point. Okay, can I assume you guys can do this, or do you want me to formally verify the properties?
We can do it.
Okay, great. Yeah, so this the rotation.
It is
Once
cos
again,
theta x minus y cos theta.
where?
X cos theta minus y sin theta.
Here.
Yes.
Why? So let's just verify for this point. Right? This is 1, 0. Where will this point go? Somewhere here. What is the coordinate of this point? And let's say this is x comma 0 rather than 1 comma 0. So what would be the coordinate of this point? What is this?
X
cos theta comma x sin.
Right. Cos theta comma
X
X
sin
sin theta.
right. So do you think this would be x cos theta minus y sin theta?
Yes.
Yes. Okay, good. Anyways, I think minus
In second one it will be x sin theta plus y cos.
right. We'll see how to verify this, right? By the way, there is a particular way in which you have to write this, and how to get this is something we will look at hopefully in today's class itself. Okay, so right now I think you should just try and verify if this is right or not. Right? And it's easy to do. For example, instead of x0, what happens if you take this point 0 y? Okay, so if I rotate this by theta, what is the point that I get? What is the x coordinate of this point?
Minus y sin
minus
theta.
y sin.
Minus y. And y coordinate?
Y cos theta.
Okay, so which is why it would be x cos theta minus y sin theta. Okay, and x sin theta plus y cos theta. Anyways, we'll look at this in more details later. Okay, another example of linear transformation. So let's say we have a matrix A of size m cross n with real entries. Okay, then I can, via matrix multiplication, I can think of this matrix as a function going from Rn to Rm, right? Okay, so A maps x, some vector x in Rn to the vector Ax in Rn. Is this a linear transformation?
Yes, sir.
Right, so it's easy to see x goes to Ax, y let's say goes to Ay, x plus y will go to A of x plus y, which is using distributivity of matrix multiplication, it is this. And similarly for homogeneity, you can verify. Any particular doubts here? So basically what we have shown here is any matrix multiplication is a linear transformation. Okay? Let's look at a different example. This is differentiation of polynomials of one variable with real coefficients with degree at most n. Okay, to itself. So this is in principle an example of a linear operator. Okay, so yeah, but first of all, of course, please verify whether this is linear or not. Will this be linear?
Yes, sir. It satisfies both additivity and homogeneity properties.
Right. So this also is linear. Okay. Let me give another example. F from to R to L to R defined as uh, notations. How about this? You've seen this somewhere?
Convolution. Convolution.
Convolution.
Convolution. Is this linear? So I hope you remember what is this L2R?
Set of absolute integrable.
No, this is not set of absolutely integrable. This is square absolute integrable. Okay. So finite energy signals in terms of signals and systems. So is this linear?
Yes, sir.
Again, when you're saying yes, I hope you're verifying additivity and homogeneity.
Yes.
Okay, so this is also a linear transformation. And there are several other ways to define a linear transformation. H from, let's say, the vector space of all ill-valued functions to itself. and h of f at t is just ht into f. Okay, is this a linear transformation?
Yes.
Say
Sir,
yes.
sir, last function definition is I don't understand.
Which one? Fifth.
Th of f t.
So for
Example, sir.
every, so if I, this one or the fourth one?
Fifth one, sir.
Fifth one. So let's say this is my vector space V. Right? Then for all f in V, th maps f to a function in V. Right? So it's a function. I can define the function by specifying what is the value this function takes at every t, which I am defining it in this way.
Okay.
So it's basically like a pointwise multiplication.
Yes, sir.
Okay, and h, of course, I've not specified here, but h is some specific function from the vector space. All right.
Yes, sir.
Okay. Let's look at another example. T from C to C. T maps x in C. Tx is equal to x complex conjugate. Is this linear?
Yes, sir.
Yes, sir.
Okay, so please remember when you are checking for homogeneity, the scalar could be any complex number as well. Okay, don't assume that it is a real number. So is this linear?
Oh,
I couldn't hear you properly.
no, it is not.
It is not linear.
Yes,
Which property does it not satisfy?
homogeneity.
Homogeneity. Okay, what does homogeneity say? T of Ax. By definition, what would this be?
A into T of
No, by definition. Your definition in the sense where this is my T of Ax would be Ax complex conjugate, right?
this is not equal to A into X conjugate.
Okay. So this by definition is this, right?
Yes, sir.
And then x is equal to A complex conjugate Tx,
T of f.
which of course is not necessarily equal to ATx. Is that all right?
Sir, here can't we have to define field?
So the field is C, right? That's what I said.
So these both are the so vector space.
Yes.
I mean, if field is R, then this is true.
Then yes. So, but that is why I said, please remember here the field is C. If it is R, then yes, it is linear. Okay, so this is just to show the importance of field, right?
Yes, sir.
Clear?
Yes.
Yes.
I think I am through with all examples that I can generate. Sort of seen all kinds of different examples, I hope. I think we can move ahead then. Okay, so linear transformations we have seen basically is a vector space homomorphism, and which is analogous to a group homomorphism. So therefore, there must be also something like a vector space isomorphism, right? Which is an analogous concept to group isomorphism. So vector space isomorphism is nothing but a function between two vector spaces that of course preserves the vector space operations, but also similar to group isomorphism, this function between the two vector spaces must be one-to-one and on-to, or basically an invertible linear transformation. Okay, so we say two vector spaces over the same field F, U and V are isomorphic if there exists an invertible linear transformation between them. Okay, invertible is just basically another way of saying that this is bijective. Okay. Right. So this is just saying the same thing again, preserving the vector space operations, and if we are given such a particular T, okay, by such I mean an invertible linear transformation between the vector spaces U and V, we call such a T an isomorphism between U and V vector spaces, and the vector spaces themselves are said to be isomorphic. Okay, so I hope you can see this is basically similar to your group homomorphism and isomorphism concept. Right. So then let us try to show, okay, that two vector spaces U and V over the same field F are isomorphic if and only if they have the same dimensions. Okay, so this is sort of different compared to groups, in the sense we cannot say that two groups which have same number of elements are necessarily isomorphic. But we cannot say that. But as far as vector spaces is concerned, two vector spaces over the same field are isomorphic if and only if, so it's a two-way implication, then only if they have the same dimensions. Okay, so let's try to show both ways. Okay, so U, by the way, I think I missed the notation here. Okay, let me write it over here. If U and V are isomorphic, this is denoted by U congruent to V. Okay. So if U and V are isomorphic, we are supposed to show that the dimension of u and v are the same. How do we show that? Anybody wants to try this?
Take any vector in first vector space.
Once again,
Take any vector from first vector space.
okay, let x be in U, then
There exists a unique combination of a unique linear, like it can be written as linear, like in the form of basis.
let's say beta I,
And this is unique.
where beta I is the basis of U. Okay, then
And applying any transformation T of x,
any transformation,
some linear transformation.
then
This will be equal to sigma alpha I T of bi.
okay,
So from this we can say that the dimension of second vector space is less than or equal to,
no, how?
it can like a linear combination of n vectors. It is written as linear combination of n vectors.
Okay,
So the
but
dimension cannot be,
no. But are you saying that this is going to span my codomain vector space V?
yes.
How? You said any linear transformation. So I can have a linear transformation P from U to V, which is defined in this way. For all x in U, Px is just the additive identity in V. This is also a linear transformation, right? Okay, so the catch is you cannot take any linear transformation. Instead, see, what do you want to show? You want to show that the dimensions are the same. What do we mean by dimension?
Cardinality of the basis.
Basis, right? So let us say beta u is a basis of my vector space U. Okay, and let's say beta u is written in this way: beta 1, beta I, where I is coming from an index set. Okay, what can we say about the set T beta I? For each of these T beta I, by definition, oh, okay, wait. I should first talk about what T I am using, right? So I'm given that U and V are isomorphic, right? What does that mean?
There exists one term onto function.
There exists a function T U to V such that T is invertible and linear. Okay,
Now,
so let
sir,
us,
if we apply this T to all the bases, then we
right.
can say that all the answer will be linearly independent.
Yeah, can we say that? What can we say about this set, which is a subset of V? Let's call it for now, I don't know, T beta U. Is T beta
All
U linearly
elements will be
independent?
all elements will be means distinct, that we can say.
But will it be linearly independent?
Yes, sir.
Why? So again, try to show this by contradiction. So let alpha i's be scalars such that summation alpha I T
T
beta
beta.
I is additive
You
identity.
can take T common,
Exactly.
and this would imply that bases are beta U
Correct?
set is linearly dependent. Okay.
Yeah. So there's one more thing left, right? Can T map, so T maps theta to theta, but can it map anything else to theta?
No, sir.
No. Since T is injective, this implies summation alpha I beta I has to be 0 or theta. But then this implies all alpha i's should be 0 since beta u is a basis. So therefore, what have we shown? We've shown that T beta u is linearly independent in V. Does it span V?
Yes, because it is the function T is 1, 1, 1.
How do we show that? So let's say there is some vector y in V. Then I want to be able to show that y can be written as a linear combination of elements from T beta u, right?
Yes, sir.
So if y is a
Right.
vector in V and we know that T is invertible, so
There exists X belongs to D.
exactly such that Tx is equal to y. Then since X is an element of U, of course I can write X as a linear combination of my bases, right?
Yes, sir.
And then Tx will be equal to alpha I T beta I, which is by definition equal to y. Therefore, y is in the span of T beta u, okay, which implies that the span of T beta u is V. And so therefore, what have we shown? That the dimensions are the same, which is what we wanted to show. Does it make sense?
Sir,
Yes.
have we defined T to map additive identity of U to additive identity of V? Or
Okay,
is it
so
or is it a
good
property
question.
of linear
Yes.
terms?
So yeah, maybe this can be discussed over here itself. Let's talk about any linear transformation. Maybe that is an example I missed. Let me add it here. So forget isomorphism, right? We are looking at only linear transformations as of now. Okay, so can you tell me, or can you give me an example of a linear transformation from R to R?
Sir, T of x is equals to a non-zero scalar times x.
Why non-zero?
No, it can be any scalar, any scalar.
Sorry?
It can be
For
any
any,
scalar.
okay. For any A in R. So this is linear, right? I hope all of you can see it. How about this? Let's call it T1 from R to R. Yes, and it is defined in this way. Tx equal to Ax plus B for some AB in R. Will this be linear?
No, sir.
If B
Not
equal to 0.
exactly. So T1. T1 is linear if and only if P is 0. Okay, so you can see that by definition over here in this simple case, T has to map 0 to 0. Right? How about in general? T from U to V. T is any, so I'm giving you that. Assume T is linear. Then what is T theta U equal to?
It should be equal to theta.
Why?
Because if it is not equal to theta, then this the property of T of something x plus y equal to T of x plus T of y will not hold.
Or what case?
Sir, we can write T of theta as T of 0 dot u.
Yes.
And that will be equal to 0 dot T of u. Homogeneity.
Exactly.
And that is equal to theta for any T of u in V.
Right. Also, you can derive the same thing using additivity. What would this be equal to? What would T of minus x equal to? By homogeneity?
Yes, sir. It will also be equal.
Okay.
Yes, sir.
So remember, any linear transformation has to map theta to theta. And of course, when I'm saying theta to theta, I'm referring to the respective or the corresponding additive identities. Okay, this theta and this theta may not be the same. Is that clear?
Yes, sir.
Okay. Right. So I hope then that answers this question that you had, right, Tarang?
Yes, sir. Yes, sir.
Okay. Okay. What is the other way around? So we are given that the dimensions of U and V are the same. We need to show that U and V are isomorphic. How do we show that? Okay. So let beta U and is beta I going from 1 to, so let's say this dimension is equal to some n. Okay, so this is n and alpha v equals alpha I also going from 1 to n. be the basis of u and v respectively. Okay, that much I can surely say from whatever is given to me. Agreed?
Yes, sir.
Okay. Now define. So basically, if I have to show that u and v are isomorphic, I need to come up with an invertible linear transformation, right? So define T from u to v as follows. T maps beta I to corresponding alpha I from 1 to n. And I'm specifying that T is linear. And my claim is this T is an isomorphism. Can you show why? So what do I need to show if I have to show that T is an isomorphism?
T is 1 to 1.
Is 1 to 1. So, and on to, right? So, can you try to see if that is the case?
Yeah, it is 1 to 1.
How? So, let, I don't know, x1 and x2 be vectors in U with tx1 equal to tx2. Can you show that x1 has to be equal to x2 then? By the way, is the definition of T clear to everyone? Do you see something wrong in my definition, or are you happy with this way of defining T? If I have to define functions between two sets, I need to specify for each element of my domain set, what does that function map this element to? So have I done that? And is this a well-defined function?
Yes, sir, because beta u spans u and alpha v spans v. That's why it is for all the points in u, the map is automatically defined for this.
Exactly. Good. So maybe explain this once again. If I say, so T to begin with is a function from U to V. In this first line, all I'm doing is specifying what T does to a particular basis of my vector space U. Right? But it doesn't specify what T does to any other element, right? Which is not in the basis set beta U. But then in the second line, I'm specifying that T is linear. Using both of these, I have specified what T does to each and every element of my vector space U. Okay?
Yes, sir.
Okay. So if Tx1 is equal to Tx2, then
T of x1 minus x2 is silent.
okay, but then what?
So if x1 is alpha I bi and x2 is
Say x2
x2
is
is
some gamma I
gamma I.
beta I. Then
x1 minus x2 will be alpha I minus gamma I into beta I.
And that can happen only if
all alpha I minus gamma I equal to 0.
right. So which means alpha I equals gamma I equals 1 to n, and that of course implies x1 is equal to x2. Okay, so this is how we show t is 1 to 1. How about on to? So let's say y is some arbitrary vector in the vector space V. Then you already have a basis of V, right? So I can write y as a linear combination of, oh sorry, I think this is a poor choice of notations. Shouldn't have used alpha here. Can somebody suggest some other, maybe AI? Because alpha is I've already, as you can see in the top of this slide, I've used that notation for the basis. Right. So y can be written as some alpha. Here also, I should use maybe gamma I, alpha I. Then what? What is alpha I?
Sir, T beta I.
T beta I. Good. Then using additivity and homogeneity. Okay, and what can we say about this element?
This is X in some.
Belongs to
This is
U.
some X in U.
Right. Therefore, T is onto, which implies T is invertible. Okay. Is that clear? And once you have two vector spaces over the same field which have the same dimension, these two vector spaces are isomorphic. And similar to the case where we had group isomorphism, right? Group isomorphism implied that one could just substitute one group in place of the other. Right? If there are two groups which are isomorphic, let's say G1 and G2, if you're finding it difficult to understand G2, maybe because the elements are complicated, then you can as well understand the group structure of G2 by understanding the group structure of G1. The same holds true over here. There are the same dimensional vector spaces. Okay, so in some sense, the cardinality is the same. So if you're finding it difficult to understand vector space V, okay, and when I say difficult to understand vector space V, I'm talking in terms of its vector space structure. Okay, only that much. So if that is the case, you can first understand the vector space structure of U, and then you can just substitute the names of the elements. Okay, so that would be an easier way to understand vector space V. I will maybe give you an example here. So, yeah. Let's say I define V to be this vector space structure, span of sine t and cos t, where t is defined between, or t is just r, okay, over r. All right, what is the dimension of this vector space? Anyone?
2.
2.
2. So maybe I don't understand this vector space clearly. Can you give me another two-dimensional vector space over R?
R square.
R square, right? Which is sort of something that we all are used to right from our school days. So by our proposition, this vector space V is isomorphic to R2. And in principle, what I can do is I can define an isomorphism in this way. T maps, let's say cos T to 1, 0, and T maps sin T to 0, 1. So that what this will help me do is I can easily visualize my sines and cosines in this way. So this is my cos T, this is my sin T. And if you recall any of your communication or signals and systems course, you draw these kind of diagrams, right? Phasor diagrams, perhaps you recall that term. Yes or no?
Yes, sir.
Yes.
So that comes because of this isomorphism. Right? This makes it very easy for you to visualize and understand these vector spaces. Okay, so every point here in this R2 is basically representing a function. Okay. This point over here, which is sort of basically 1, 0, is representing the function cos t. This point over here, which is on the xy plane, just 0, 1, this is actually representing the function sin t. So on and so forth. Does it make sense? And of course, I think it's an undeniable fact that the xy plane is something which is very intuitive compared to this vector space V that I've defined over here. All right.
Yes, sir.
Okay. So I hope you understand what is a vector space isomorphism. Now, when we introduce this concept of linear transformation, remember the first or second example we took was that of, right, a matrix multiplication, right? So here we showed that any matrix multiplication, right, is a linear transformation. Okay. How about the converse? Is any linear transformation basically a matrix multiplication? Right? If that is true, then it justifies why why engineers spent so much time analyzing matrices, right? I mean, it sort of emphasizes the importance of studying matrices. Okay, so is that true? Is any linear transformation a matrix multiplication?
Yes, sir. For every linear transformation, we can define a matrix of that term. We can find a matrix.
So can you do that for convolution? This fourth example that you see over here. Fourth or fifth, whichever you want. How do I write this as a matrix multiplication? Sorry?
Here, h of t and f of t are functions.
Right. But you just said any linear transformation I can represent using matrices, right? So, and we have proved that both these examples are linear transformations. So,
It will be the 1 cross 1 matrix f of t.
So, but
H of t.
f of t is h of t or f of t. Both of them are not just one numbers, right? They are functions. So, can I write this as a matrix? So I guess what you're trying to say is for each t, this is a matrix, so or a scalar multiplication. Is that's fine, but the entire linear transformation as such cannot be written as a matrix multiplication that way, right?
Yes, sir. For vector spaces, we can easily define.
Easily defined. Can you?
Easily find the matrix transformation.
Okay, so is there somebody else who wants to give his or her views on this? Okay, the question that we are trying to answer is, we have shown that any matrix multiplication is a linear transformation. Is the converse also true? Is any linear transformation a matrix multiplication?
For this case, if f of t is represented by a sequence,
Sorry, if f of t,
can f of t be represented as a sequence?
no, it cannot be, right? Because the domain, I mean, it's a function over R, right? And R is uncountable. If it is uncountable, of course, you cannot write it as a sequence. If it was a discrete sequence, I mean, it was in the terminology of signals and systems, if it was a discrete signal, then yes, you could write it as a sequence. But even then, I would argue and sort of say that you cannot write it as a matrix, or because a sequence is still an infinite sequence, right? I mean, there are infinite numbers. Doesn't make sense to say that the size of the matrix is infinite. Krupal, you had something to add?
Yes, sir. I was saying about discrete case, but we generally have limited signals in signal system. Here you are saying for longer infinite time, so it is not working.
So what do you mean by limited signals?
Means signal which starts by zero and end at some point. Like we examples which we used in class. We used to do figurative convolution by just flipping the signal and then multiplying step by step
Mhm.
by delaying time. So we had some sort of matrix multiplication.
Acha, okay. Okay. So for finite signals, as you're saying, you possibly can, but if it is continuous time, then
Then I am not sure. I was like
right.
comfortable with this thing.
Okay.
We can write it in discrete. We can write.
Discrete you
If
can
we
write.
if we find the Fourier series representation, then it will become discrete.
Yeah, but how many Fourier series coefficients would it have?
That's the problem. If it is infinite,
Right.
infinite sequences, then it will be.
Good. So good. I'm happy that you're sort of almost there. So the issue is, as you will see now, the dimension of the vector space. It's not just the number of elements in or number of numbers that you use in order to represent an element of the vector space. It could be functions. For example, this vector space is finite dimensional. You give me any linear transformation here, I will come up with a matrix. Okay, so the problem is not whether it is continuous time or discrete time. Problem is the dimension of the vector space. So to begin with, let us assume that we are given a linear transformation between finite dimensional vector spaces. So I don't know whether I've introduced this notation. FDVS will stand for finite dimensional vector spaces. Okay. So let's begin with that. Of course, I'm not putting any limit on what that finite dimension is, but it is some finite dimension. Okay. So let us begin with a linear transformation T between two vector spaces U and V. Okay, and let us say the domain vector space U as this spaces U1 to UN, and the codomain vector space V as a basis V1 to Vm. N and M can be any arbitrary numbers. They need not be the same. They can be the same. It doesn't really matter. All right. Then, right, for any vector x in my vector space U, of course, because I have a basis, I can represent x as a linear combination of that basis U1 to UN. And I'm interested in, of course, finding what is the output. Okay, so when I use output, you can sort of think of T as a system, a linear system. So for this linear system T or linear transformation T, when X is the input, let's say Y is the output, that can be written in this way. T applied to that particular linear combination. And then using additivity and homogeneity of T, you can write it as this linear combination. Is that okay? This should be straightforward.
Yes.
Now, one important conclusion that we can draw over here is, see, if I don't say that this T is linear, so let me replace it by some function notation U to V. Right? Irrespective of whether U and V are vector spaces or not, if I want to specify a particular function from U to V, how do I do that? Right? The only way to specify a function is I have to specify what that function does to each and every element of my domain U. Right? Maybe there are functions that I can represent using formulas, exponential, sine, whatever, but there also are going to be functions that I may not be able to represent them in such a nice way, right? Therefore, the only way in which I can specify a general function between sets U and V is by specifying for each element of U, which of course there may be infinitely many of them. But the only way in which I can uniquely specify a general function is by specifying what it does to each and every element of my domain. Compare this with this equation where the function between these two vector spaces U and V is also given to be linear. In that case, if I want to specify what T is, right, what can we conclude from this particular equation here?
We should specify what it does to the basis of first vector.
Great. Right, you can see that once I know what TUI is, I know everything there is to know about T. Right? Because this AI, of course, has nothing to do with T. It has to do, it comes from how I represent the input X in terms of the given basis. So as far as specifying or designing a linear system is concerned, the job is much easier. The number of variables is much less. The number of parameters is reduced drastically. The only thing that is left in designing a linear system is to figure out where this linear system will map the basis to. Right? And since you have, or you're doing signals and systems in the same semester, compare this with a linear time invariant system. What does it mean to design a linear time invariant system? How do I specify a particular linear time invariant system? Can someone tell me?
So we need to know just a
Impulse
impulse.
response.
Exactly. So what is impulse response? It is what the system does to only one input. A particular one, of course, but still, I need not know what that system does to each and every basis. I will come to know that if I know what it does to that specific input. Right? So under that context, I hope you see the importance of linear systems. Okay, and these days there is this disease of machine learning and deep learning, which also utilizes this. Okay, so please have this in mind, right? Why linear systems are so popular? Because designing them is not a very tedious task. You need to specify only what it does to the basis and you are done. Okay, so it is sort of flexible and also not very, the number of parameters are also not huge. Clear?
Yes, sir.
Okay. So then, like as I just said, PUI, only knowing these n outputs are enough to know output for any other input x. Okay, that is what we just said. Now let us go further. What can we say about PUI? By definition of T, PUI also belongs to the codomain vector space V. And for that codomain vector space V, I already have a basis. Right? So therefore, I should be able to represent each PUI as a unique linear combination of my bases V1 to Vm. Okay, and since there are two variables here, I and j, so the scalars, okay, also I have to sort of equip it with two subscripts, j and I. This could be a possible source of confusion, but I hope you can see through this. Right? Each TUI will have possibly a different linear combination of my bases V1 to Vm. Okay, so therefore I cannot just write it as Cj Vj. So each I, the Cjs will be different. Is that clear? So then just substituting this over here, I get y, which is what I want to find out, is a summation of ai into this is my tui. Okay, so I can of course gather the summation together and then I'll get this. Okay. Now the thing is to bring this into a matrix. See, what I want to do is I want to sort of specify this linear transformation. So assume that the vector space U and V have these bases fixed. Okay. Once these bases are fixed, so what I mean by fixed is, of course, there are infinitely many choices of bases for the same vector space available. But once you choose one basis, you don't change it. So once you fix these two bases, you don't have to keep on specifying the basis itself, right? Instead of x, right, I can represent x by its coefficients. Similarly, y can be represented by its coefficients, let's say b1 to bn, right? This is unique because we have a basis. So instead of finding what is the relation between x and y through t, I can specify the same relation t by specifying the relation between the coefficients. Agreed?
Yes, sir.
Yes.
So what is the relation between the coefficients of x and coefficients of y? Right, so as I just said, y will also be a linear combination of vj, and we know that the linear combination is unique. So would this linear combination and this linear combination be any different?
They are same.
They are same. So what can you say about, let's say, BK? What is BK in terms of A and C? Remember, BK is the coefficient associated with the kth basis BK. What would that be over here?
Summation I equal to 1 to n AI CKI.
CKI. And this is true for each and every K, right? So K can go from 1 to
N.
not N. How many B's
M.
are there?
Oh, M.
M.
Right? And this, if I write it as a vector, right? A's remain the same. What would be over here?
Sir, a matrix whose columns are transformation of basis of first means U.
So that is right. BK. So let's say B1 is equal to C11A1 plus C12A2 plus C13A3, so on and so forth, C1NAN. So that's your first row times this vector A. This is B1. Similarly, B2 is C21, so the second row times the same vector A. Okay, so this matrix is basically called the matrix representation of the linear transformation with respect to beta u and beta v. This will be my notation. Okay, so this is the representation of my vector x in the basis beta u. This is the representation of the vector y in the basis beta v, and these two are related via this matrix. Okay, so the notation is the square bracket argument, whatever is inside is the actual linear transformation. Okay, the subscript denotes the basis that I have chosen for my domain. Okay, and the superscript denotes the basis for my codomain. Okay, we'll stop here for today and we'll further analyze this on Friday. Okay, so thank you and sorry for taking 5 more minutes extra. See you guys on Friday.
Sir,
Yes.
sir, I wanted to ask, is there any difference between therefore and implies, or we can use any of them anywhere? Both are same or any difference?
Therefore, I have to think about it. Don't have a precise answer for you right now, but let me think over it and I'll get back to you maybe on Friday or before that.
Okay.
Sir,
Yes.
sir, I have a doubt relating presentations.
Okay.
As you said, you will call any random person and ask to present. So what if we cannot present? We could not able to answer your question.
Then you get penalized. What else?
The entire group or a single?
Hopefully the single person, but I mean, I've not yet thought about the marking scheme as of now. So yeah, I'll have to also be consistent with my co-instructor, Professor Rahul Muthu. So I'll discuss with him and then maybe let you know. But as of now, I request all of you to prepare fully as if each one of you is going to present the entire project. Okay, so in case you have not, any particular person in the group has not understood something, it is his or her responsibility to discuss the doubts and issues with other group members. And so as of now, I have not thought about your question, whether the entire group will be penalized or only that particular person will be penalized. So as of now, I don't have an answer to you. Instantaneously, my thought suggests that I would not penalize the entire group, but as of now, I'm not committing to that.
Okay.
I've also received a request for an extension in the deadline for project report submissions. I will discuss it with Professor Rahul Muthu today and maybe send an email tomorrow latest. Okay. Right. So then see you guys on Friday.
And in this